So this video lecture is based on a question I received about standardizing and rescaling the predictors and how to interpret the estimated coefficients. And in order to answer that properly, I am creating this video. Okay, so we are in the linear regression framework. We have our data set. And we have our design matrix, which is consists of all these rows. Each row is one observation, and then we have the responses, 1 to n, and we talked about this a lot. We want to estimate the coefficients, and we minimize the residual sum of squares, and if you do the math, this is what we get. This is our beta hat. This is the linear regression coefficients we get. Now the question is, how do these coefficients change if we had standardized the predictors? Again, the question is, how would these coefficients change if we had standardized the predictors? Okay. So what does standardizing mean? In order to answer that question, we need to reformulate a little bit. And the reformulation is as such. We have p columns, and each column we call it phi, phi1, phi2, phi p, and this is in contrast to the n rows we have. So we can have n rows or p columns, and each of the columns is one predictor. So therefore, and since we want to standardize the predictors, I need a formulation which refers to the columns. So phi I is the ith column of X. Let Si be the standard deviation of the ith predictor. So this is the jth column, right? X1j, first row jth column, second row jth column, third row jth column, nth row jth column. Sj is the standard deviation of the jth predictor, and x bar dot j is the sample mean of the jth predictor. So x bar j is the sum of all the values of the predictors. Xij, ith row, jth column. So we look at all the rows of the jth column. We look at the sample mean. And this is how we find the sample standard deviation. The summation is over all the elements in the jth column. So how are we standardizing here? We divide the predictors by their standard deviation. So the first column is divided by the standard deviation of the elements in the first column. The jth column is divided by the standard deviation of the jth column, and the pth column is divided by those. So once you divide that, make that division, you have a different design matrix, which I will call X tilde. Let's see if we can write a matrix multiplication into X that gives us X tilde, and that is obtained by having this matrix S, which is a diagonal matrix, S1, S2, S3 to SP. So all we need to do is multiply X by the inverse of S. S is diagonal, so the inverse is just 1 over S1, 1 over S2 to 1 over SP. This is the first column, so this will be multiplied by this. This 1 over S2 will be multiplied by this, and this 1 over SP will be multiplied by this. Okay, so X tilde is just a multiplication of these two matrices. Now, when we fit a regression model to the standardized coefficients, we are solving this problem. We are minimizing, we're finding the beta that minimizes X minus X tilde beta. So beta tilde is just X tilde transpose, X tilde inverse, X tilde transpose Y. And X tilde is just XS inverse. X tilde is XS inverse, so it's XS inverse transpose, XS inverse, and the whole thing inverse times XS inverse transpose times Y. Now recall, for symmetric invertible matrices, A inverse transpose is A transpose the inverse of A transpose. So here, and also the other thing is that AB inverse is B inverse A inverse. And I guess that's all we need. So XS inverse transpose becomes S inverse transpose, X transpose, X S inverse, the whole thing inverse. And XS inverse transpose becomes S inverse transpose times X transpose Y. S inverse is symmetric, so S inverse transpose is S inverse. S inverse transpose is symmetric, so S inverse transpose is S inverse. So we end up with this formulation. Now we want to take these two out of the inverse, and we are using this identity that AB inverse is B inverse A inverse. So what we are doing is saying, okay, let's call this A, S inverse X transpose X as A, and let's use S inverse as B. So then we will have B inverse here, which will be S inverse inverse times inverse of this, which is S inverse X transpose X inverse. And then S inverse inverse is S, and then we have S inverse X transpose, and then we do the same thing again. We apply the same thing again, so this becomes our A, this becomes our B, so then this becomes B inverse, and then S inverse inverse becomes S. So this whole quantity is S X transpose X inverse S. The S with the S inverse cancels, so we ended up with the S X transpose X inverse X transpose X, and that's just beta tilde. So to summarize, if you are fitting this regression model, which is unstandardized, beta hat is X transpose X inverse X transpose Y. If you standardize the predictors, beta tilde is just S times X transpose X inverse X transpose Y. This is beta hat, so it's just beta tilde is S beta hat. So beta tilde, so the coefficients that you would get after fitting a linear regression model to standardized predictors are the same coefficients that you would get from the unstandardized predictors times their corresponding standard deviations. In other words, to get the standardized coefficients, you simply multiply the corresponding standard deviation. So that's why in one of the lectures I suggested that in order to compare the size of the estimated coefficients, just fit the model as is, and in the end, if you want to see which predictor is more important, which predictor is less important, multiply them by their corresponding standard deviation so you get a unitless quantity that is comparable. Okay? Okay, so this was about standardizing, this short lecture.